One, everything you say can and will be used to tease you in a court of law. Just kidding. Welcome, everybody. Today, we're going to talk some more about circuits and how we draw them in AutoCAD. So today, the first thing we're going to talk about is analog versus digital. Then we're going to talk about why that's relevant to our control circuits. We're going to go over a couple of examples interspersed all through this. We're going to talk about some PLC and control system architecture as a whole, because we haven't really touched on that yet. And it's important to help understand these things in context. And then if we have time, I want to at least talk about communication standards as it applies to control system architecture. So analog versus digital. So these are just definitions I found on the Google. Analog is related to or using signals or information represented by a continuously variable physical quantity. And then digital, in modern day computing, everything's digital. And basically that just means a binary value, right? It's 1 or 0. And when you combine that into bits and bytes, you can quantize some physical value, right? Which is an analog value. So that's kind of vague and maybe not super helpful. So let's dig into this a little bit more. So an analog value is a continuous spectrum. So it's infinitely divisible. You can keep going to higher and higher resolution. And the physical world around us is completely analog, right? So anything you encounter in nature has some extent of degree. And a good example of this is color, right? The light wavelength is on a spectrum. It's a direct result of the photon frequency, right? But what we can see lies on a spectrum. And for any given human, they have a specific spectrum that they can see. But that spectrum that they can see is pretty much infinitely divisible. So any frequency in that spectrum, you can change it a little bit and it'll be a little bit different color. So just off the top of my head, some more examples of these are like metal composition, right? You can purify a metal, say iron, but it's still going to have trace elements of other things. So anytime you have a metal sample, that's really kind of an analog value, because it has, even if it's purified, it still has trace amounts of other things. Another example would be heat flux. So in these engineering classes, we're usually talking about steady state systems, right? And they have a specific heat flux, but in reality, like there's going to be a little bit of variation there, right? And you could say the heat flux is 1 joule, right? But it could be 1.00001 joules, and it's infinitely divisible, right? The amount of heat moving through your defined area. And a third really great example of this is how annoyed your life partner is with you at any given moment, right? So for me, that value is usually pretty high, but it's in constant variance, right? And it's on a spectrum of like a little bit annoyed to very annoyed. And the other thing about that particular value is it's sometimes very difficult to measure. So in a circuit, an analog value, it'll be an input or an output from a module. And that value, that analog value, is a way of, it's tracking some physical property, right? So we'll get into the examples of that later. But it's really a measurement of the intensity of a value or the degree of something. Okay, so on the other hand, we have digital values. And as I said before, digital values are bits. They're on or off. They're a 1 or a 0, right? And so sometimes these are referred to as discrete, right? Because it's a very, very quantifiable thing. right? The light is on or the light is off. There's no degree of on or offness of the light. It's either the circuit's closed or it's open, right? And so in the modern age, computing is done using physical arrangements of transistors. And a transistor is a fancy switch that's either on or off. And so if you're familiar with CPUs at all, for example, like AMD Ryzen CPUs have close to 6 billion transistors. I'm not going to comment on that particular chat point about AMD versus Intel. I'm just trying to give you an order of magnitude scale for how many transistors, how many on and off values there are in a modern CPU, right? So in small scale computer or consumer electronics, like a washing machine or your dishwasher, the number of transistors is going to be really small in that CPU. It might be on the order of thousands. I don't really know off the top of my head, but if you have a high quality modern CPU in a computer, it's going to be on the order of billions of transistors. We're going to talk a lot more, or not a lot more, but some more in a future discussion about transistors, how they work, and their applications. But moving on, most of the circuits we've looked at this quarter are discrete circuits. So they can basically be represented as a digital value of on or off, closed or open, right? So a good example is a watch. So if you have an old school watch with gears and hands, that's an analog value, right? Because it's constantly sweeping through that value. Whereas if it has a digital, like an LCD display that shows actual numbers, that's a digital value because it's a discrete value. It's one finite number that's being displayed. So why are we talking about this, right? Why is this important? Well, historically, there have been analog computers, and so if you look at this relic on the left here, this was recovered somewhere in the Mediterranean, if I remember, and it dates back to the Bronze Age. And if I remember correctly, this was used for like computing taxes or something. I don't remember. But it's an analog computer. And then here on the right, you have a more modern era example of an analog computer that's from the 50s, I think. I don't remember exactly. But there have been analog computers, and in a few specific applications, they still exist. And in some cases, you could kind of say that a lot of modern instrumentation is really a small analog computer. Now, one of the issues with analog computers is once you make it, it's a physical configuration of dials and gears and all this stuff, and it's very, very specific. It has a very specific purpose that it's manufactured for, and it's probably hard or impossible to adapt it to a different purpose. They can also experience physical degradation, which will cause drift in their computing operations and can lead to inaccuracies. And then, it's only as good as what you put in. And so they're kind of more subject to user error. So if you're like adjusting dials and knobs and you don't get it in the right spot, you're going to get a bad value out of this thing. So those are a few reasons why analog computers are less common in the modern era. But you're still going to run across analog measurements all the time because you're in modern instrumentation, like for example, a temperature probe, you're measuring a physical value, right? Like we said, the physical world around us is all analog values. And so when you're taking a measurement, you're measuring an analog physical phenomenon. And then what you're going to do is you're going to have this train of modules and instrumentation that converts that analog value into a discrete digital value in your computer. So as I mentioned before, a light switch is a good example of on or off, right? Now you might be thinking, well, that light could be different brightnesses, right? And that's true. So what if we added a rheostat to our circuit? Does anybody know what a rheostat is? Don't everybody speak up at once.
I'm guessing it measures Rio.
So a rheostat is a fancy word for an adjustable resistor. So this is a picture of one. I'm going to switch to the overhead real quick. So if you have your circuit, and you have a resistor in there, a rheostat, the symbol is like this. So it's just a resistor with an arrow through it. And so what this is it's a physical wire winding. And then it has what's called a wiper in line. And this is on a movable armature. And then it's got a wire lead coming off of it, right? And so you can actually move this wiper in and out along this wire winding. And so what happens is you have your incoming current, right? And then you're actually changing the length of wire that current is traveling through, because it's coming in, it's going up this arm and out here. Let's just say this isn't connected. Don't worry about that third leg. So as you move this wiper back and forth, if the wiper is attached here, the resistance is low, right? Because it just comes in and it bypasses all this winding and it goes straight up. Whereas if the wiper is attached here, it has to go through a much longer length of this wire winding, and so the resistance is higher. And so if you remember from physics class, your voltage is equal to your current times your resistance, right? And if this is fixed, so generally our voltage is going to be fixed at 24 volts DC, right? So if we're changing our resistance, our current is going to change inversely. So as resistance goes up, current goes down, and vice versa. So in this circuit, this is a diode, which is pretty much going to emit a constant light intensity. So let's say we have your conventional incandescent light bulb, like you have at your house, in line with the rheostat. So what happens when I come in and I adjust this rheostat? If your current's changing through here, what's going to happen?
Brightness of the light changes.
Exactly. And so this is high resistance, low current, right? And then if you lower your resistance, it gets brighter and brighter and brighter. So that's literally how your dimmer switch on a light in your house works. It's a rheostat. So most potentiometers use a rheostat, or at least historically they did. They might use a different technology now, but your typical cheap off-the-shelf run-of-the-mill potentiometer is going to be a rheostat. Anybody know what a potentiometer is?
It's a knob.
It's a knob. It's a fancy word for a knob. So it just means that it's measuring the position of the knob that you're turning. And so this has a huge number of applications, right? But what it does is it's adjusting an analog value on a spectrum. So those come in a couple different forms, but that's a really great example of how, you know, you have this discrete on or off, but if you add a little bit of complexity to your circuit and add a rheostat, you can actually turn that into an analog value as well, right? Because now when you have your rheostat in line, you're changing the intensity, you're changing the degree of light that's available. So if you look here, this is kind of a nicer schematic than what I'm able to draw by hand. And so you have your current in, and you have your wiper that's adjustable along this coil winding, and then you have your current out. And most of these rheostats or potentiometers come with 3 connection points. So you could have your current come in on terminal C and then out terminal B, or you could have it come in terminal A and out terminal B. It's just a matter of preference whether you want it to increase or decrease in reverse or forward. That's the only reason they have 3 poles. But hopefully that's a little bit better image for you to understand what I'm trying to draw. Okay, so moving on. Another example, a relay. You guys remember we talked about relays last week? It's a electromagnetic control switch. So is a relay a discrete or an analog device?
Discrete.
Discrete, exactly, because it's on or off, right? It's open or closed. So fun fact, transistors are essentially function very similarly to relays. And so they've kind of, in a lot of applications, they've actually replaced relays. And we'll talk about that again more later on. So the third example I have for this is a motor speed output from your control module. So if you're changing the speed of a motor, is that an analog or discrete system? Going once, going twice. Nobody? Okay.
Analog.
Yep, it's analog, right? So typically motor speed is measured in rotations per minute. And if you're changing that speed, it's analog because it's on a spectrum. It's from 0 to whatever the maximum speed your motor can run, right? That might be 3,500 RPM, right? And everything in between, really, you can divide that into an infinite number of values, right? So even though it's usually reported as an integer value, really it is a spectrum. So that's another example of an analog. So real quick, let's talk about the standard voltages or standard types of discrete and analog that you'll encounter in our control systems. So for digital or discrete inputs and outputs, you can have 120 volts AC, and then we're going to have 24 volts DC. Sometimes you'll see 48 volts or 12 volts, but usually it's 24. So what are some pros and cons of using 120 AC versus 24 volt DC? Anybody? Okay, so one of the advantages of AC is that you don't get voltage loss over distance. So if you're just running short distance control signals, 24 volts DC is going to be fine. But if you're running in the hundreds of feet, you might actually get degradation in your voltage just from the resistance in the wire, to the point where when you energize that circuit and close it, I'm going to switch to the overhead again real quick. So that's not good. Bear with me. I don't know why this keeps happening with my camera. It's super frustrating. There we go. So if I have my circuit, then I have some, let's just keep using a diode. Actually, you know what? I'm just going to make this a contact. And then I have a switch here. So here, this voltage potential is 24 volts. But when I run through all this wire, this may have degraded to like here across this contact, 18 volts or even lower, right? And if this module here on the receiving end is sensitive, if it has a threshold voltage of like 22 volts, this signaling may not work, right? Because when I close the contact and complete the circuit, it's only seeing 18 and it needs 22. So this is a drawback of using DC voltage in long distances. And so in some heavy duty industrial facilities, this discrete signaling will actually be done using 24 volts AC. And that's because AC does not, shut up Siri. AC doesn't have that same degradation over distance. That's another reason that long distance power transmission is done in AC, because you don't see that voltage degradation over distance. Now the downside of using AC is that typically it's much higher voltage, and it's dangerous. So anywhere where you can use a lower voltage, you want to go ahead and do that because it reduces risk to your operators. Because anytime there's some kind of physical damage to the system and you have an operator exposed to it, you have the potential to have a safety hazard. And that can be a really big problem if you just have tons and tons of high voltage running all over the place, especially when you have electricians in there troubleshooting everything. If it's 24 volts DC, you're safe to go in there with pretty minimal protection and test out your circuits, see where you might have issues. If it's 120 AC, you have the potential to really harm somebody. Okay, so that's discrete, digital on or off. Now analog, your typical standards, what you're gonna see mostly is 4 to 20 milliamps. Less common, but it's still around, is 0 to 5 volts DC. And there's a distinct advantage for having 4 to 20 versus the 0 to 5. And the reason for that is you can do what's called loop powering of a device. So if I have a controller, a PLC here, and then I have some instrument out in the field, and this needs power, what I can do is run power on this wire, and then I'll have a return here. And this is a 4 to 20 milliamp signal, right? And so what's happening here is this instrument is controlling the amperage output back to the controller that it's sensing. And so what you can do is do what's called loop powering, where all the power, all the juice that this instrument needs to run correctly is being supplied to it in this positive leg. And then this device is taking that, powering on, and then returning current on this scale, this 4 to 20 milliamp scale, back to the controller, which the controller is reading as an input, as an analog in. Analog in. So this is a huge advantage, because if this were to be 0 to 5 volts, well, now my instrument can't really use that for power, because this instrument's going to want to see a constant voltage in order to run. So that's one huge advantage of the 4 to 20 over the 0 to 5 volt. Now, the circuitry for 4 to 20 internally on this instrument is generally going to be a little bit more complicated, a little bit more expensive. But in modern day, it's still fairly cheap. And so it's always better to go with 4 to 20. It just gives you a lot more flexibility. and a lot less wire to run. And so again, if you're running 100 foot of wire, using a 4-20 may actually save you a lot of material costs for your wire. So another analog signal standard used to be pneumatic pressure that was run from 3 to 15 psi. And so you could actually just take a pneumatic tube and run it between control modules, and you'd have complicated valving and manifolds that controlled air pressure, almost like a modern day automatic transmission uses fluid pressure. And you'd actually use that for analog signaling between modules. And so these days, that's pretty rare. As you can imagine, there's inherent issues with it. If you have damage to your tube, you lose air pressure, your system really doesn't work anymore. And it's much easier to damage pneumatic tubings than it is to damage wiring. So nowadays, you still see that 3 to 15 psi, but it's really only on control valves that are pneumatically actuated. And what happens is there's a little module on the valve, and it's called the I to P transducer, so current to pressure transducer, and it'll take a 4-20 signal and use that to control a small regulator valve in that box that controls the pressure to the valve between 3 and 15 psi. And so you might be asking, well, why don't you just use an electric actuator on that valve? And you can buy valves that have that, but those electric motors to control that valve position are way more expensive. So it's way more cost effective if you have industrial compressed air supply available in your plant to use air to control your valve stem position, and you just have you have to size your valve correctly, and it'll have dampening and return springs in the valve, so that you can just control from 3 to 15 psi on your valve and get your desired position. So I think in a future lecture or future session, we might actually go over control valves a little bit more in detail. It's interesting and useful, and it's kind of important to understand, especially for us, because we deal with control valves all the time as chemical engineers and process engineering. And there's a myriad of valve types and actuator types. So we'll probably talk about that more later this quarter. So the last type of analog signal that we're going to deal with is 0 to 60 hertz. And this is going to be an output directly to a motor. We talked about this a little bit before, how you can control motor speed. The way you do that is you actually vary the frequency of the sine wave AC output to the motor from your motor controller. And so this is definitely an analog value, right? You can change that frequency anywhere from 0 to 60 hertz. Depending on your system. Some systems you might go even higher than 60 hertz, but typically what you're going to see is 0 to 60 hertz in the US of A. And so this is our final example of an analog value. It's very important. We actually have this on our demo PLC panel that we're going to be using later. So we're going to go more in detail on this later. Okay, so how does all this relate to us? We're kind of talking about a little bit of ancient history, what may seem like tangents right now. So it's really important to understand these things because pretty much all modern computing is digital. Because digital models are cheap, they're readily available, they're generally fairly programmable, right? So they're more flexible than an analog computing device would be. And for us in this seminar in Chem E CAD, we're kind of exploring how we measure things with instrumentation and how we control things with a programmable control system. And so again, really this boils down to that translation from a physical, real-world analog value to a discretized digital value in a controller that we can then do some math with and then have outputs depending on what that value is. So a good example that I've already referred to a little bit is temperature. So for those of you that have done, I think the fall quarter junior chemical engineering lab, you've actually made a J-type thermocouple. For those of you that haven't got there yet, essentially this is just two wires, two different kinds of metal wire that are welded together to form a junction. And the J-type just refers to what those two metals are. And what this does is it takes advantage of what's called the Seebeck effect, where that junction actually produces a voltage potential dependent on the temperature of the environment, or actual temperature of that metal junction. So when you submerge that into a hot fluid or a cold fluid, the voltage across that junction is going to be different. And you can hook that up to a little computer module and measure that voltage change, or that voltage potential at any given temperature. So hopefully it's stable so you can actually measure it fairly well. So what you do is you connect the tail end of those two wires that form a junction to a voltage reader module that's really sensitive, because this is going to be on the order of 0 to 70 millivolts for a type J. And that module is then hooked up to a computer. And so somewhere between those two modules, the computer and the voltage module, there's going to be a translation of that voltage into an actual integer value. And so you're taking that analog voltage value, right, which is really reflective of the analog temperature value in the real world, and you're digitizing it into an integer value that can be stored on a computer. So for a lot of instrumentation, the memory block for that is going to be like 16-bit, which gives you 0 to 65,000 discrete digital integers that you can have. Now, if this is an 8-bit system, you only get 0 to 255. So even though you're measuring the same spectrum, right, 0 to 70 millivolts, your resolution of that value when you digitize it is much lower depending on how much memory is allocated to storing this bit, right? And so that becomes very important, because your accuracy of your measurement is inherently tied to the resolution when you do that digital conversion, or that conversion into a digital value. So generally speaking, for temperature, you know, if you're within half a degree, you're pretty happy. And so that digital conversion isn't that big a deal. But when you're doing really, really sensitive laboratory experiments, this starts to get really important. And so it's important to know, you know, not only how accurate is the calibration of your instrumentation, but how accurate is that digitization of your measured value. And so you explore that actually hopefully in pretty good detail when you do that lab. When I went through it, we had a really good TA that really harped on the importance of looking at the sampling frequency and a few other things in order to get consistent measurements. So typically when you do that analog to digital conversion, it's going to be at least 16-bit, and it'll be an integer type, but don't quote me on that because it's totally dependent on your controls hardware. It could be a floating point value. It could be 8 or 12 or 16 or 32-bit. It totally just depends on the manufacturer where you got that hardware. Okay, and so the last step of this is, okay, now I have an integer value. It might be 50,000. It's whatever. That's now scaled into in the computer, translating that into something that a person can read, right? Which is going to be some temperature scale, let's say degrees Celsius. And so through all of this, let's say my measured range is, I'm going to switch to the overhead again. Which zoomed out, but that's all right. Okay. So let's say I have an RTD probe that's resistive temperature device, right? And it's in a bath of hot water. And then that's connected to my voltage module. So actually in an RTD, this voltage module is going to be integral into the instrument itself. It's going to be housed. It's a little control circuit board. Come on, camera. Keep getting blue screen. There we go. So there will be a little circuit board inside the housing of this RTD. Stay still. And that'll do that conversion for you. And it'll put out a 4 to 20 signal. But let's just say, for the sake of argument, we're just going to show this in our schematic. So 0 to 70 millivolts. This can be 0 to 750 degrees C. That's output to our controller as 4 to 20 milliamps. And then from our controller, now this is all happening inside this controller. That says inside right there. View my beautiful handwriting. So inside here, this gets translated to 0, 65K, 16-bit values. And then that finally gets translated into some temperature value that's displayed to the user on a screen, on an output screen. And so you see here, there's all these translations that happen through our train, from the physically measured value to some analog value that's an electric signal, right, which then gets translated into our standard control signal, our standard analog control signal, right, that then gets digitized into some digital value that then gets translated out to the end user. Now, in our control scheme, this is great. This lets somebody actually read this, but if this is an automated controller that needs to respond based on this measured temperature, it's going to look at this value and it's going to input that into some control algorithm that we're just going to represent as a squiggle box. And then it's going to have some output into a physical real world system. So this could be like a cooling water circulation to cool this down, or a heating coil to heat our water sample back up. I lost my slides. Okay, so this is another pretty cool little example. So you've probably all seen one of those circular pressure gauges with a dial on it, right? That's represented by this schematic right here. And you may or may not know how this works. So basically, internally, there's this tube called a board-on tube that's shaped like a shepherd's crook, kind of. And that's connected to your external pressure system. And so the cross-section of this tube, taken, if you can see my mouse moving across this cross-section here, looks like this flattened oval shape when it's not under pressure. But then if you increase the pressure in this tube, it becomes more circular, less flattened due to the internal pressure. And what that does is it causes the shepherd's crook to actually straighten out and pull up. And then that goes through this mechanical linkage and this gearing, and it makes that needle that indicates pressure move. So this is another analog device. So how would you change this, and instead of a human readable format, how would you get this into a computer as a digital value? I'll give you a hint. It's written on the slide.
Using a rheostat.
Exactly. You got it. Good guess. So if you put a rheostat on the physical pivot point here, that would get twisted as the needle twists, you could use that as an input into your control module, and you can measure the position of this thing based on the resistance in your circuit, and you can calibrate that directly to a given pressure, right? And so if you do this, you're going to introduce a little bit of actual physical resistance to your system because of that extra mechanical linkage. And overall, this isn't like the highest precision way to do this, but you could actually augment an existing mechanical system you have already as an input to your control system. And that's just another example of how you can translate a real world analog value into a digital input signal to your controller. Okay, so the last thing we're going to be able to cover really quick is I'm going to go back to my overhead. And we're just going to talk about control systems architecture. Whoa, that's weird. There we go. Still don't know why this thing keeps zooming out. Okay, so for us, we keep talking about this PLC. So this is our math box. Does a lot of things, right? But this is our computer. This is going to be where we program math, where we measure one state and output another state. And on this PLC, there's these auxiliary modules that you can just clamp onto the side that are your I/O, right? They're your inputs and your outputs. Spelling, output. So you can buy all different kinds of I/O modules, depending on what you need. You can get relay contacts, you can get all different kinds of voltages. There's all kinds of things that are industrially available. And so if this is your inputs, you'll have termination points that wire to things like RTDs. And they might wire to something like a pressure sensor. And they might wire to something. And so those are both analog inputs to your controller. They might wire to a push button. Right, and that's a discrete input. God, I can't write. So a push button would be a discrete input, right? It's open or close, okay? And then over here in your outputs, your O module, so you're gonna wire to things like lights, right? We talked about that earlier. You might wire to a VFD, a variable frequency drive, and that's a discrete output. Now this in turn takes an analog output from the controller and it outputs a sine wave to a motor. Okay, so these are the kinds of inputs and outputs that you'll connect to your controller. And then also off your controller, you might have a touch screen or a monitor screen or something, and that, like a monitor and a keyboard. And so that's your human machine interface. So for your laptop, your HMI is your keyboard, your mouse, your microphone, your little tablet drawing input that I don't have that I really wish I had for this class because it'd make it much easier. That's your human machine interface. That's important. And then also off of here, you might be communicating with some kind of control module that's maybe more specialized than your PLC. So for example, you could have a temperature controller that's another control module, right? And that's actually attached to an RTD. And it's also attached to a heating coil. Okay, and so this is an output, this is an input to this module, right? And the reason you might do this is there's a lot of very cheap, commercially available temperature controllers out there. I think the Chem E Car Club got one for like 20 bucks one time. And so this has instrument input from the field, and then it has an output to some control device, right? Let's say a heater. And it's doing some math in here where it takes this input, runs it through an algorithm, and gives this output, right? But then you can also have an output from this controller into our PLC. And so that's another analog value, right? That's probably a 4 to 20. And so this can be a 1 or 2-way communication path where I can push down a set point to this controller from my PLC, or I can just monitor this value so I know what temperature it's reading here. And I could also monitor what the output is. And so I might have this temperature control module directly controlling my field temperature, but then I'm monitoring the temperature in my PLC. And based on that, I might do something like, for example, energize a cooling fan as well from my PLC. And so these two control modules are kind of working in tandem. And there's all kinds of mathematical models for how you would actually do that inside the controller. But it's important to be aware that your control system might be made up of multiple controllers, which might be more or less sophisticated than an actual PLC, okay? And then the final connection that I want to talk about is a PLC is generally used for kind of one system. So that might be like an air conditioner or a heater or a bank of fans or a reactive system or something, right? But usually it's going to be what's called, or a lot of times it'll be what's called a skid-based controller. And so you'll buy a specific specialized system from a vendor that's a skid-based system. And what that means is it's just on a metal frame that they built at their warehouse, and they ship to you, and you bring it in and you set it down and you connect some process piping to it, and then it's ready to go, and it just works from the factory. And so that'll usually come with a skid-based controller, which is usually a PLC. Now, if you have this big industrial plant where that's just one unit operation, right? So let's say an air compressor, it's a skid-based air compressor. Well, you're also going to have a plant-wide control system that there's different platforms available. Common platforms are called a SCADA system, which is supervisory control and data acquisition. There's platforms that are called BMS, building management systems. DCS is distributed control systems, which is really like one giant PLC for the entire plant, which is really common in oil and gas systems or oil and gas plants, or PAAs. Pick any acronym you want, right? I'm sure there's plenty more control system acronyms out there. But the important thing is, this is just another layer, another onion layer of control system It's kind of symbolized by, you know, this local temperature controller and this PLC that's kind of the higher level control system. And so you'll have another connection to, for example, your SCADA system. And again, you might be pushing down operating set points from your SCADA system, right? And you're also almost for sure communicating up your key operating parameters, which could be temperature, pressure, flow rate, whatever. Or maybe you're just reporting your local set points that somebody came and entered into this controller from the HMI. Somebody came and typed in, I want this temperature, this system here, this water, I want this maintained at 100 degrees C, okay? They type that in here, go to the HMI, it goes into the PLC, gets pushed down to the temperature controller, and simultaneously gets reported up to your SCADA system to let you know, hey, somebody, Bob, just logged into your HMI and told this temperature controller to maintain 100 degrees C. And so in pharmaceutical plants and whatnot, all of this gets validated, and a lot of times that reporting of process set points gets recorded into the data historian that's part of the data acquisition of this control system, and it gets put into batch reports, and ultimately that kind of stuff is submitted to the FDA. So hopefully that made sense and wasn't too confusing or rambling. This stuff in my world and my previous experience has been super important. And you can see this overall architecture is what we're going to be drawing in CAD. We're going to be hopefully finishing up our set of drawings for our control cabinet this quarter, and you're going to see some stuff like this. Any questions?
What was the M at the end of the squiggle?
Motor.
Oh, that's just the motor itself. Okay.
Yeah, so this would be your 0 to 60 hertz signal that I kind of referred to earlier. And so this, yeah, that's kind of the end of the line. There's some circuitry in here called motor windings that I'm not an expert on at all, but they respond to different AC frequencies and eventually get translated into motor spin speed, or RPMs.
So if this is a temperature control system, that would be the motor that actually controls the fan or whatever it is.
Yeah,
or thing.
It might be, yeah, it might be like a fan blowing across cooling fins to cool it down. It might be a liquid circulation pump that was circulating hot or cold fluid. It might be a physical actuator that just opens or closes a valve
Okay.
to control fluid flow. And that's an interesting point, actually. A lot of times in fluid systems, those pumps are just run at constant speed. They don't actually vary the RPM of the pump motor. What they do is, let me find a blank spot on here. So you got your pump, a little turbine, and you got your inlet and your outlet. And so this will spin at say 750 RPM or whatever, whatever the manufacturer's recommended speed is. And that's just constantly sucking. And then up here, you have a control valve. And this control valve is actually what controls the flow rate of fluid in the piping system. And literally, this could be just so if this circle represents your piping cross section, if it's what's called a gate valve, there's a circle that fills the pipe completely, and as you raise the valve stem up, it opens. Oh God, I can't draw. So let's say this is 50% open. This part is blocked, and this part is open, and so you'll have a certain basically choked flow rate through that pipe, right? And so if it's 100%, then this is fully open. Fun little tangent. Anything else? Yeah, Mason.
So my internet got disconnected.
Okay.
Like right as you were starting the drawing.
Okay.
Is there anything important that I missed? Because I can just go back and watch it on the uploaded thing.
Yeah, I mean, if this all made sense to you, I think you, Mason, specifically got exposed to a lot of this last quarter. So what a PLC and the I/O modules are. So I mean, this video will be up on YouTube, hopefully today, and you can definitely go review that. But I would guess you probably have a decent understanding of this already.
Thank you.
Yeah, for sure. So the point of going over this is just to kind of give a higher overview of how all these things connect and what the importance of each module is in our control system. Anything else?
So VFD is a variable frequency drive, right?
Correct. Yeah.
Can you talk a little more about that? Do you know a little more about that?
Yeah, and we'll probably go over this in detail in a future session. But basically, a VFD, like everything else in this class, is a big box. And what this does is it takes, in our case, it takes 120 ACN to power it. And then there's a controller on here. There's a computer. I'm going to call that a CPU. And this whole thing is a VFD. And then this is going to output some AC power. So in our case, it's 230 single phase, but it could be 480. And this is AC power. And so what it's doing is there's a transformer in here, and there's all kinds of really cool heavy duty inductive circuitry that I really can't tell you how it works because I'm not an electrical engineer. But it does awesome stuff. And so it's taking, you can just plug this into a wall socket, and it's outputting some manipulated electricity into a motor. And so if you're familiar with AC power, you know that its output has a sine wave. And so this measurement, the measurement between peaks of this sine wave, is called the frequency, which is 1/seconds or hertz. Okay. And then the amplitude is going to be proportional. Sorry, the amplitude is the measurement from this this midline, this 0 point to the top of the peak. That's going to be proportional to your current, essentially, which is also proportional to power. So I'm trying not to screw this up too bad because, again, this is not my area of expertise. So this is one of those don't trust and go verify moments. Okay, so what this variable frequency drive box is doing is it's taking this sine wave output and it's modulating the frequency between these two peaks. Okay, and so as I mentioned before, you'll have 0 to 60 hertz. Okay, and this is really an analog value because depending on your motor, so if your motor is rated for 300 or 3,500 rotations per minute, well, that's 0 to 3,500 RPM, and that's directly scaled to your 0 to 60 hertz output. And so if you dial this VFD all the way up to 60 hertz, your motor should spin at 3,500 RPM, okay? And so if you set your output to 30 hertz, that should equal 1,750 RPM. And so again, that's entirely a direct result of the way that this motor is configured internally, and the way this wiring is connected. And so the cool thing is most of these VFDs are available off the shelf, where they can hook up to, they can take a variety of input power and they can give a variety of output power forms. And most of them, for example, ours has a little LCD screen, and it's got a little knob, and it's got a bunch of buttons. And so you can program this locally from this local input, right? And anytime you take one of these fresh out of the box, you're going to need to configure it using this local touchscreen. But what you can do is you can also connect. Let's see if I can put this on screen here. So there's going to be auxiliary contacts on here that you then connect to your PLC output for a variety of I/O. So that could be like a run command, a stop command, and then an analog input that's again 4 to 20. That's an input to the VFD, which the VFD then converts into your 0 to 60. And so the reason you have this as an external box is because there's all that power transformation that has to happen in here. So these VFD boxes are relatively expensive. I think your entry level from Automation Direct is going to be a couple $100, because that circuitry is just expensive. And so you wouldn't include this by default in your PLC controller, just because it's an expensive module to have that you may or may not use depending if you're doing motor control. That may be way more than you were looking for. And like I said, we'll definitely go into this in a little bit more detail in a future meeting.
Cool, thank you.
Sure thing. All right, we're it's like about 10 minutes over time. So I'm happy to hang out longer, but you guys are free to go if you like. Cool. I'm going to kill the recording, and I will see you guys on Wednesday.